So can you hear me now?
We can hear you and see you. The slides.
Yeah, I now go to the presentation mode. It's not working.
So at the moment, what we can see is the.
Yeah, fine.
Ah, there we go. That looks lovely.
Yeah. So hello everybody. I will talk today about the liquid confined in a nanogap with the size of few nanometer to a few hundred of nanometers, and the liquids which we have are used in our experiments with the small liquids. Do I come back from the presentation mode?
Something has happened there. Yes, sorry.
Okay, I stay like
That's
this.
back.
The confinement, why we are thinking about the confinement, because the confinement is very nice tool to control the matter in a nanoscale. And I have here some examples, for instance, from the group from Patrick Huber, where we combine liquid crystals with a porous amorphous aluminum amorphous membrane and get the materials with very, very nice optical properties, which can be tuned with the size of these pores. Another examples where the confinement can be used is crystallization of organic crystals from solution by applying a pressure. These crystals have different properties and shape, as you can see here. These two examples can be used in electronic industry, but the confinement and especially crystallization in confinement can play a big role in the tribology, also in the case if we want to control the chemistry on nanosize. And if we talk about the liquids, we should first start with the water, because the water is the most important liquid for us. And I would say that water is involved in confinement on a natural scale. Also, we have a lot of technologies, like for instance, the water desalination, where the crystallization in confinement is very important. Now I want to explain you what we understand under confined induced crystallization. So this comes from the work from Klein and Komacheva, and they study OMCGS in surface force apparatus, and they observe solidification. Solidification is an unambiguous establishment in the confined experiments. It's very well known that with confinement, the viscosity increase a lot, which leads to increasing the relaxation times. And just to give you an idea what's happened before the confinement, the liquids is like a liquid, but after confinement, we see a solid film, and this process is irreversible. And so Klein and Komacheva, when they observed this solidification, they suggested that the geometrical constraints can lead to crystallization. And this put a lot of discussion in the community, which continue in nowadays, what is actually the structure of the solid phase. And nowadays, we know very well that the structure in confinement is mixture of disordered structure and also layering on the surface. And now we're talking about the crystals in confinement. These crystals have two aspects. On the one side, the matrix can support the crystallization and give a shape of these crystals. Also, it also can influence the crystal phase. But the question what I would like to address in our experiments is really to prove if the confinement itself, the constraint itself can induce a crystallization. For this, we use liquids with the small molecules which don't have self-assembly properties, and the interfaces which don't have a strong interaction with these liquids. Before to go to the experiments, I want to say a few words about the simulation and the theoretical development. These simulations are very important for understanding of the confined matter. Unfortunately, the experimental evidence cannot follow them. The reason for this is that the confined samples are very small and they have this heterogeneous structure. And with this, they put a strong demands on the sensitivity of the experimental methods. Nevertheless, I show you here one combination of experimental work and simulations where crystallization of the colloid particles is proved under optical microscope. And the simulation shows that with decreasing of the gap size, different crystal phases can be observed. Another thing what I want to point out is that the theoretical investigation shows that crystallization should happen due to the entropy excess. But all examples, experimental works shows that the pressure play a very important role in the confinement. Therefore, I think that the pressure is still not understood in this process. And to conclude this, I have to say that the simulation and the theoretical investigation really support the crystallization in confinement, and more experimental results are needed to prove this. So I show our experiments and start with the experimental setups. We have two of them. One of them we call diamond cell. So since we confine the liquids between two diamond anvils, the cell is equipped with the top and side microscope, and you see the pictures on the right side from the both microscopes. And we create the liquid in the cell by condensation of the liquid at the top diamond. The another cell is a so-called stem cell. Here we can confine the wafers with 5 by 5 millimeters, and we compress them by the stem on the top and measure the pressure with the pressure sensor on the bottom. And here the liquid crystals are created, the liquids films are created by drop casting. In the experiments, we measure the reflectivity, perform reflectivity scans and in-plane measurements. In the in-plane measurements, we shoot with the beam through the gap and put the area detectors, or we perform in-plane scans. And from the reflectivity, we measure the film thickness, and also we extend the reflectivity to higher Q values because we are also interested in the signal which is coming from the layering. This layering has a size of the short range order of the liquids. Therefore, it is appear in the Q range where the structure factor of the liquids are. In the in-plane crystallization scattering, we focus mainly on the searching for crystal peaks. Here I present you the result of OMCTS and TMS. Actually, mainly from TMS, but the OMCTS behaves very similar way. I have to say that this liquid solidificate very fast, and evidence for this is that the thickness which we get on the when we confine is defined from the size, from the amount of the liquid which we have on the substrates. And once we get this film, it is very difficult to compress it further. To get films with different thickness, we open the gap and put a new liquid inside, and so we create a layer after layer and become thicker films. And this kind of samples, we never observe for crystal peaks, but we could observe a very nice layering even at the higher films with a higher thickness. In the case of water, it's completely different because the water can be compressed. So here I show you, we create a film with 75 angstrom and with one confined a sample, we could go down to 16 angstrom, and that's why because of these properties, that's why I believe that the water is almost not solidificate in confinement, and this gives a possibility to create in one sample very thick and also very films where the layering of the water could be observed very nicely. Well, if you're talking about the crystallization, we do observe single crystal peaks in the confined samples of water in both cells, in the diamond cell and in the stem cell. We compare these results with the samples which we call empty samples. It means that we close the gap or confine the substrates without the liquid inside. And this ensures us that the peaks which we observe are coming from the liquid confined in the substrates. Moreover, the Q values which at the positions where we observe these peaks cannot be assigned to the crystal structure of the substrates. Therefore, we believe that the crystals the peaks which we observe are coming from the crystallization of the water. About the
Milena, just 1 minute, please.
Yeah. About the carbon tetrachloride, we have studied this extensively, and we find out that it crystallizes in rings if we have thick films. It crystallizes in powder if you have thick films. And in the case of thin films, we observe a single crystal reflections like in case of the water. And with this, I come to the conclusions that we are pretty convinced that the carbon tetrachloride can crystallize in confinement. In the case of water, we also observe a single crystal reflections, and we believe that water is crystallizing in confinement, but we would perform more experiments about this. In the case of MCTS, we believe that there is no crystallization, since these two liquids solidificate very fast, and this prevents the building of the crystals in the gap. What I also want to say is that it is very difficult to repeat the single crystal reflections from one experiment to the other experiment. That's why we suppose that the surface structure and morphology is very important, play a big role in this process. And with this, I want to thank you to your attention. And I want to stress that this is work, in-house work, and I thank to my colleagues, Oliver, Zek, Anita, Ines, and to the teams of Beamline P8 and P23, where I performed the experiments. Also, I want to thank to our contribution from Kim Nøgaard, and also the nice cooperation with the group from Patrick Huber, and thank you to the organizers to giving me opportunity to give this talk.